Okay, so it's lecture 4. Sorry the video's not that great, but you can see my face, that's fine. It's September 8th, 2016, and this is NRGY 101. This is the first of 3 little 20-minute lectures that I'm going to give, and I want to kick this off with a problem that I just call the banking problem. Now, I'm going to try to use a smart board, so just bear with me 1 second on the technology, and I'm going to try to get that running here. Just give me 1 sec. I haven't started up I'll just pause this. Okay. Well, while Tim's getting that, I'll just explain it in words. Okay. So I'll just explain it in words, and then I'll write it down. So get your notebooks out. And so it's a word problem, or or a story problem, if you will. And this is something that we'll see more of throughout the semester, but I just want to get you started on this. So imagine you've got a wealthy relative, rich aunt, rich uncle, and they're going to give you, not really to your knowledge, they're going to give you $1 a minute. So they're going to put $1 a minute into a bank account for you from the time you're born, right? So, and then we're going to assume that you're going to live to be 100 years old. So what you need to do is figure out how many dollars you have when you're 100 years old. So.
I watched this lecture online.
Did you? Okay, well.
I already did it.
You know the answer? Okay, well, you're probably in the minority. What's your name?
Mosey. Oh, well, it's John Gerber on that list. I just go by Mosey.
Mosey. Okay. Well, Mosey, don't blow my cover here.
Okay.
Glad you watched it though. Anybody else seen it? Okay. It's just it's kind of out there, but it's important that you go through the exercise. So, sorry, what's your name next to Mosey in the back?
Cat.
Cat. Okay. Oh, you're Cat. Okay. Nice to meet you, finally, Cat. All right. Well, give her some hints, but don't give her the answer. Okay. So I first need you to figure out how many minutes old you are when you're 100 years old. So that's kind of your lifespan. And as organisms, we all consume energy metabolically. Did Peter talk about that much at all? Like you're 25, and we'll do units later, but 2,500 kilocalories per day, and I think that's also in the book. That's how much energy you need metabolically to live. Now, humans also need technological energy, or use technological energy. We drive our cars, we fly airplanes, we're running my laptop, we've got the HVAC on the building, so we also consume energy technologically. And up to this point in our global civilization, the majority of that energy, at least since the Industrial Revolution, et cetera, has been fossil fuels, so gas, oil, and coal, and I think Peter did a good job explaining that. Now, what I want you to do is just in your mind figure out, well, where did all those great fossil fuels come from? Well, they came from photosynthesis, so sun is shining on planet Earth, life is emerging, algae, grass, trees, lions, tigers, bears, all these animals. Well, I think most of the oil is probably from non-mammalian sources, but all these plants and animals were essentially sequestered as carbon reserves. That's where it takes life in order to assemble those little carbon bonds. So now what I want you to do is think of those carbon bonds as those dollars in the bank, and I want you to estimate how long ago that bank started. So you need to write that number down too. So how many years ago did life start on planet Earth? And we'll go with the currently held scientific theories rather than sort of the more mythological theories that you might be familiar with. So now, so you got how old you are when you're 100 years old. You've got the number of years ago that the carbon bank started. So you need to write that number down. And then the third number you need to know to solve the problem is how long it's taking us to extract those carbon bonds from planet Earth. So, let's see if I can't get this guy. I'll mess with the bamboo as soon as I launch the problem. So you've got how many minutes old you are, you've got how many years old the carbon bank is, and then the next thing, this is pretty trivial, we're going to assume that the carbon bank was really sort of being extracted very quickly starting in 1863, so about 150 years ago. So that's when you start your extraction. And most of the sources that you see in the textbook will show that the majority of the oil, a lot of the oil supplies, so in North America, oil peaked a little bit in the 40s, it peaked again in the 70s, and it seems like we're kind of on the downward slide. That's why we're digging up the tar sands, et cetera. Same thing happened in England a long time ago. Similar thing happened in the Soviet Union in the 80s. That's why their economy tanked shortly thereafter. And those peaks sort of happened. We're going to assume that we're sort of at this global peak of those fossil fuel resources. So that happened 150 years ago. So you need to tell me how many years in the future they'll be depleted if we continue at the current rate. So that'll give you your third number. It's basically just 150 times 2 is the number of years that the carbon bank is being depleted. So the question I have for you is, how many minutes do you have in your lifetime? So instead of this, sort of global civilization extracting energy from the earth, imagine you're just that person going in your bank account to get your uncle's money out. How many minutes do you have to spend that money? So what's the minutes equivalent of the problem I just gave you in years? And I'll put it on pause and I'll write that up on my bamboo as soon as I get it going. So work on that a little bit and then we'll be right back. And gals, let's go ahead and solve the problem. Yeah. So here's what we'll do. Let's just start off. So Mosey and Kat, what's your either calculated number or your best guess? Just give me how many minutes you got to retire.
I'm just confused what we're being asked to find. Are we trying to find how many minutes?
Well, because we figured out how many minutes are in 100 years.
Yeah.
And then we times that by 3. So that is how many minutes in 300 years. And then we're trying to figure out.
Yeah, I think you just got a little. You got the two portions kind of on the same side of the equation. But I'll solve that. So just give me a guess. How old are you when you get to retire? 70 years, 80, 99 years? Like, I'm looking for how long?
Okay, well, so I guess if we got this many,
I'm glad to know that, Moses.
Not
I just don't
much.
feel
Not much.
clear enough.
I don't even think it's in the years.
You think it's less than, okay, so let's just say less than 1 year. Okay, less than 1 year. Marshall, Matt, you guys get a number?
We were working with them when we were.
Okay, probably, but short, less than a year, okay.
less than
Well,
a
you
year.
made some progress then, okay. Steve and Tyler, what did you get?
A misunderstanding of the question, I think.
Oh, okay.
So you're looking for how long, if you got $1 a minute, how long it would take you to retire?
How long it take you to spend all that money? Because we're spending fossil fuels pretty quickly. We're spending 3 billion years of fossil fuels in 300 years.
Approximately like 3 years.
About 3 years?
I'm trying to calculate.
Okay, so 97. Yeah, well, I don't always explain it exactly right, but you'll understand it very shortly. Robert and Mike? Nothing? Just take it, give me a guess.
That's like.
Say about 99.5.
99.5, okay, so you're like hedging your bets on The Price is Right, okay.
I was just thinking.
Well, so typically we do this problem, people are like, 70, 80, just, but it sounds like you've, maybe seen this a little bit before and kind of know that it's not long. So let me draw it out here. Sometimes a picture helps. Let's start with a picture. Yes, most of us are kind of graphical thinkers. So what we're looking for is, I'm just going to go with 3 billion years ago. You could also put in, someone said, let's put in 350 million. I mean, and all we're going to do is kick that 0 one notch over. So there's 3 billion.
All right.
No problem. And here's now, so 3 billion years ago. And I told you that we're going to burn all, so 1860 was about here. And then, 300 years is here. So this timeline is in years. And so I said, well, let's just compare this carbon bank to a money bank. And you might say, well, most of this was actually laid down, somewhere in here, or maybe it was here, depending on where life was, flourishing the most. There were extinctions and all that, and interruptions. But now let's do this instead in minutes. And this is basically when you're born, and I'll just say this is 100 years ago. But we're going to do it we'll do it in minutes. And so now we're here at time 0. And the question is sort of how long is this little retirement party? We're just going to compare those two lines. That's really all we're doing. So how many minutes old is a 100-year-old person?
52 million.
52 million.
My guess goes down even less than.
Oh, okay.
Yeah, it was 52.
It's in the minutes.
Yeah.
We only have like a few minutes to spend.
Yeah, well, there you go. So I'm just going to write that out as 50 million. We'll just round it because, you can get very precise, but obviously this problem is just meant as an illustration, not an exercise in significant digits. So what we're going to do is put the carbon on this side of the equation, and these are dollars down here. So here, this is going to be my little equation box right in the middle. We'll put carbon on this side of the equation. So here's 3 billion, and that's in the bank. That's the deposition, and on top we'll put our extraction, 300, and years and years. So don't forget the units. Equals. Now our money bank we were measuring in dollars, but it was sort of the same as minutes because we were putting in $1 a minute. That was 50 million minutes. So now the question is, what goes in this box? How many minutes are we looking at? So do that math for me, and we'll know the answer. Yeah. So once you see it, and that's kind of the way almost all these word problems are. They're like, what the heck? It's confusing at first, but then it just boils down to one little equation, and you solve it. So what's the number of minutes? And one way I sometimes do it is just you can knock off these two zeros. Knock off these two zeros, and just end up with a ratio, and this ratio actually becomes 10 million to 1.
What you're going to find with these little word problems, if you watch, Brad and I solve them completely different. He likes to do one huge equation with like 50 numbers in it and cross cancel. I like doing it step by step so I can figure out if I screw up one place, it's easier for me to find them.
Yeah.
0.06 minutes.
0.06. Who's got another number?
6 seconds.
6 seconds. I come up with 5. 5 because 300 is to 3 billion as 1 is to 10 million.
So 5 minutes.
5 minutes is the same.
Is how long it takes.
Yeah.
That's a smart way to figure it out.
Yeah. So
It's just a 1 to 10 million, so how many?
there it is. So
Yeah, that makes so much more sense.
yeah, so there you go. Okay, so this problem, I mean, it just boils down to just one equation, one unknown, and you've all had algebra by now, or you're taking it, and it's just they don't get a lot simpler than that in terms of solving the math problem, and it just comes down to some fairly simple arithmetic. So the take home here is like, yeah, in a sense, we were born yesterday, you know? You know, in terms of the amount of energy that has been stored, you know, more or less on trickle charge, and I think you all know what trickle charge is. You've probably seen them on top of campers or boats or whatever, even maybe used in your car. You've got the little solar panel out there trickle charging the battery. The Earth has been on solar trickle charge for a long time. You know, and here we come, you know, drill baby drill, frack baby frack, dig, you know, dig, etc. And we're going pretty gangbusters into that bank. And if we are at the peak of that, which, you know, the book seems to imply based on a lot of engineering and scientific evidence, it's really time to figure out, well, what's our best strategy? Do we leave those fossil fuels in the ground for future generations? Do we just, you know, use them all up as quickly as possible and then get on with the renewables, or somewhere in between? So that's kind of the take home on that. All right, so I'm going to pause that lecture, put it in the bank, and then I'll get on to the next the digital bank, the digital archives. And all these lectures are on YouTube as well. You'll see them pop up in the shell. And Peter's are all there as well.